All right, so the topic of today's class is Java generics. All right, so remember previously in the course we implemented a stack. So the first stack that we implemented, what did we do here? The first stack that we implemented with an array was a stack of ints. Right? And so when we implemented the class, there was an array inside the class, right? So an array of int that held the elements of the stack. When you push an element onto the stack, right, it's a stack of ints, so the input type is int. And of course, when you pop something off the stack, it's a stack of ints, so the return type is also an int. Right? Now, suppose you wanted a stack of something else. So suppose you want a stack of strings, right? You can't use a stack of int to represent a stack of strings. And so one solution is to make a separate class called string stack or something like that that can hold a stack of strings. Right? So imagine what this class looks like. So there's our stack of int, and there's your stack of string, right? And notice the things that are in gray, those are the only things that change, right? So the name of the class changes, because you can't have two classes with the same name in the same package, right? The array type changes, right? It's now a stack of strings, so you now have an array of strings. Pushing something onto the stack means you push a string onto the stack, and popping something off the stack means you pop a string off the stack. Right? And so there's almost no change to the code. It's really just in the types that are related to the element type. You might say, well, okay, so the methods didn't change very much, but maybe the implementation of the methods changed. Right? And so if you go and look at the implementation of the methods, again, almost nothing changes. Right? So for the pop method, well, you return a string, and of course the element type now is just a string instead of an int. Otherwise, nothing changes. Similarly, is there push? Push is similar, right? So push an element onto the stack, almost nothing changes in the implementation. So the only things that are changing are related to types, right? Basically, you're substituting string for int in a few places, right? And if you're in a situation like this, you might ask the question, well, my compiler's kind of pretty smart, so maybe the compiler can do this work for us. Right? Maybe it can just substitute string everywhere where it needs to, where there used to be an int. Right? That's not how it works in Java. It is how it works in another language, though. So in C++, this is exactly what the compiler does when you use C++'s version of generics. Right? The compiler actually makes a new class for you and then makes all the type changes for you. Right? Java generics work in a different way, but they are similar. It's a similar idea. Okay, so before generics were introduced into the language, generic collections were just implemented as collections of objects. So before version 5 or 6 of the language, I don't remember anymore, you used to be able to write code that looks like this. Right? So here I have an array list. Now notice here I don't use the angled brackets and say what the element type for the array list is. It's just array list. Right? And when I make the array list object, I just call the array list constructor, and again, I don't use the angled brackets. Right? How do you use this thing? Well, you just use it like a list. So I can add the string hello to this list, right? And I can print that list. You get this if you run that code, right? So it prints the list containing the string hello. Right? I can now add the number 1, 2, 3. So this gets converted to a big I integer object. Right? So auto boxes the 1, 2, 3 to a big integer, adds the big integer reference to the list, right? And if you print the list, you get hello 1, 2, 3. So it works, right? So this looks a lot like a Python list now, right? Where you can put anything you want to in a Python list. And so this is the way generics used to work in Java, and it still works this way, right? Notice this is a modern version of the Java compiler, right? It's running. I don't remember which version of Java it's using. Java it said there a second. I don't remember. It's like Java 11 or something like that. Anyway, it doesn't matter, right? This still works, right? The reason it still works is because there's all this old existing Java code that used to be written this way. And so rather than break all of the old existing code, the language designers came up with a way to make the generic types a little easier, safer to use without breaking the old existing code. In new versions of the code, you'll get a warning when you try to do stuff like this. Right? The warning you get is that array list is a raw type. Right? References to generic types should be parameterized. Right? And so you're not supposed to do this anymore, but it does still work. Right? And so the way these used to work is that an array list would just be an array list of big O object. And you know you can put anything into a list of objects, right? And so instead of making a stack of ints or a stack of strings, you could just make a stack of big O object. Right? So this one uses our list implementation of a stack. Right? So here I've got an array list of big O object. Right? When I push something onto the stack, I'm going to push an object reference onto the stack, and when I pop something off the stack, I'm going to pop an object reference off the stack. This works fine, except it's inconvenient to use. Right? And so the problem is that you've got a stack of objects. So when you pop something off the stack, you get back a reference to an object. If you want to use it as its actual type, now you need a cast. Right? So for example, here I've got my stack of strings. Well, a stack that's supposed to be only strings, right? But internally, it's represented as a stack of objects. So I can push a bunch of strings onto that stack, right? Now, as the user of this class, I know that I'm only pushing strings onto the stack, right? So when I pop the stack, I know for sure I'm getting back a string. Right? Unfortunately, the compiler thinks you're getting, the compiler gives you back a reference to a big O object, right? If you want to use the returned object like it was a string, now you need the cast. Right? So now this works, right? So every time you're popping something off the stack and you want to use it, you need the cast, which is a little inconvenient. But there's a bigger problem, and this is a problem that's shared with the Python language. There's no type safety. So any reference can be pushed onto a stack of objects, right? So if I make this stack of strings, I can push whatever I want onto this stack, right? There's nothing stopping me, or there's nothing, the compiler can't help me if I push an integer or a double object or a date or something else onto the stack, right? So there's no help from the compiler here. The programmer has to be very careful that they're only pushing what the element type they think they should be using for their stack onto the stack, right? And that leads to problems like, oh, sorry, this is fine. Right, so here, same example, I've got a stack of what I think is just strings, but I can push a 1 onto the stack, I can push another stack onto the stack, I can push a date onto the stack, I can push whatever I want onto the stack, and it's going to work. Right. The more serious problem is that it's impossible to write what are called type-safe methods if this is the way that you're implementing generics. Right. So imagine that I want to write a method that, what does this do, sums? Yes, that sums the elements of a stack. Right? And here, I'm assuming that the stack contains a bunch of integer objects. Right? You can write the method, no problem. Right? So this is going to do sum and clear a stack. So basically, it's just going to pop all the elements off the stack, and it's going to sum the elements as we go. Right? There's an assumption here that this is a stack of integer. Right? So it's easy to write. Right? You start with a sum of 0. Right? While the stack is not empty, pop the stack. Right? Now remember, this is a stack of objects, so when I pop the stack, I get back an object element. Right? Now I need the cast because I want to add because I want to treat them as integers. So now I cast the element to an integer, add it to the sum. Right? The problem with casting is if that thing there is not a big I integer or an int, the cast will fail, and you'll get an exception. Right? So there's nothing stopping somebody from passing. Oh, someone. I don't have it here. Okay. So there's, if someone passes you a stack and one of the elements, or one or more of the elements of that stack is not an integer, that cast fails and now your method fails. Right? So there's no way to write type-safe methods if you implement generics this way. What you really want to do here is you want that thing there to indicate that it is a stack of integer. Right? And so that's what the modern Java generics do. So the way it works in Java is, you've seen already, you don't give your class a different name for every type, right? So there's no int stack, string stack, date stack, et cetera, et cetera, et cetera. Right? Instead, there's this extra parameter that you need to supply when you use the class. Right? So instead of int stack, you write stack and then the angled brackets and integer, right? Where the integer is the element type held by the stack. Right? Stack, angled bracket string is a stack of strings, and so on and so on and so forth. Right? So these types of generic classes are type safe. Right? If you change that from list object stack to stack of integer, you know for sure that the only things on that stack are integers. Right? And you don't need this cast anymore. And this will never fail because you've got some sort of illegal element type in your stack. Right? Okay, so how do you cook up one of these generic classes? It turns out it's not that hard. Right? So all you do when you create the class is you put in the angled brackets, and then you list how many type parameters your class needs. Right? So for stacks, you only need one type parameter, right? The element type for the stack. In general, though, you can have as many type parameters as you want. So if you have multiple type parameters, you just separate each parameter with a comma. So this looks like a list of parameters for a method or constructor. The names that you choose don't really matter. So the convention in Java, though, is to pick a very short name. So typically it's one letter, or a letter and a number, or something like that. Oh, the name that you picked, these are just placeholders, right? So they're just placeholders for that you're going to use when you implement your type. When the user actually uses your class, they will tell you what the exact type is, right? So when the user makes their class, they will say class name, string, integer, double, blah, 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 right? But when you're creating the class, you just give it some dummy name, right? Some placeholder name. So when you look at the implementation of these classes, typically you see names that look something like this, right? So it's one letter long. If it's just some type, people just use T, right? So T is very common as a name for a type parameter in these classes. If you're representing a collection like a list or a stack or something else, E is also common, right? If you remember how maps work, maps map a key to a value. So in the standard library, the map implementations use K and V for the key and value types. Occasionally, you'll implement a type that requires a type parameter that is only a number. So you might use N there for number, right? So integer, double, long, float, something like that. Okay, so how do you make one of these classes? Again, it's pretty easy to do. Right? You just, instead of writing in actual type names, you just replace those type names with your generic placeholder names. Right? The fact that Java can only return a single value is occasionally inconvenient. Right? Again, the fact that Python lets you return a tuple from a function is nice. Right? You can return a whole bunch of information from a Python function. In Java, it might be nice, so in Java lacks that feature. So if you want to return multiple values from a Java method, you have to do something like create a class that does nothing except hold those values. Right? So for example, if you want to find, if you're searching a list or a collection of some kind for the maximum value, it might be nice if you got back the maximum value. Is that it? No, so I think they might be doing a test. Yeah, I know. They did this like 2 weeks ago, right? I'm just going to give it a minute. Hopefully the flashing light stops. All right, I'm going to try to continue. If it starts to ring again, I guess it'll be for real. Okay. So when you're searching a list for an element, say the maximum element or the minimum element or some specific element that meets some criteria, it might be nice to get back the value of the element and the location in the list, right? So I want to return both the index and its value. There's no way to do that in Java with just using a single return type. Single return value, sorry. The solution to this is make a class that can hold more than one value, right? And so in this case, I want to hold two values, so I can make a class in Java that represents a pair of values, right? And the class does nothing, right? It's simply there to let you hold two pieces of information. So there's your class, right? I'm going to call the class pair, right? Now I want to be able to reuse this class to hold any two types of values, right? So I'm going to make it generic, right? My first type will be T1, and my first type will be T2, right? When someone uses this class, they will substitute the actual types for T1 and T2, right? This class does nothing except hold two pieces of information. So it has two public fields, right, called first and second, right? The first field is of type T1, and the second field is of type T2. And there is your first generic class, right? How do you use this thing? Well, it's pretty easy to use. So here's my method max that searches a list of double for both the maximum value and the location of the maximum value. So the location, right, is an integer. The maximum value, it's a list of double, so the maximum value must also be a double. Okay, if the list is empty, obviously there's no maximum value, so I can't search the list. Here I choose to throw an exception, right? Otherwise, the list is not empty, so there must be a maximum value in the list. So I just make my pair object, right? Pair result, this is buggy. There is a bug here. It's still an object, so you still need to make the object. So you make your pair object, you make your result, right? Its type is pair. So you go ahead and make your pair object, right? Now you might say, hey, there's no constructor over here, right? There's no constructor over here, so Java makes one for you. You get the no argument constructor, right? So I call the no argument constructor make a pair object, right? I'm going to assume that the maximum element is the first element, right? And if that's the case, then so I'm going to store the index 0 in first. I'm going to store the value of the maximum of the first element in second, right? And now I'm just going to search the rest of the list, right? So starting at index 1, going up to but not including the size, right? Get the element out of the list. If the element is bigger than the current max, do I have max? Oh, this one's really buggy. Sorry. Is very buggy, this one. If it's bigger than result second. There we go. Right. So if the element is bigger than result second, remember result second is holding the value of the maximum, the current maximum, right? I found a new maximum value, so set result first to I and set result second to elem. Right? When you're done searching the list, you've got the maximum element, so now you can return the result. Right? The caller will get back a pair object. To get the index, they just write result.first. Right? To get the maximum value, they just write result.second. Right? And so that's a little example of a generic class. Right? It's exactly the same as a regular class, except it has the angled brackets and the type parameters. Right? Instead of using actual type names, you use the generic parameter, the generic arguments as your types when appropriate. Right? Okay, so what about our generic stack class? So if I want to take our stack class and turn it into a generic stack, how do we do it? Right, so I'm just going to start with the array stack implementation. Right, so our array stack, our previous implementation was a stack of int, I guess. I want to make it generic, so I stick in the angled brackets and a type parameter here. Right? I'm going to use E here for element. You could use T, that would be fine too. Now before I had a stack of int. Right? Now I have a stack of this element type E, so my array type, I want it to be E. Right? So all you do is you just change, wherever you used to write int everywhere, I'm now just going to write E everywhere. Right? And so that's now element type E. Right? Now you go ahead and start to implement your class. Right? And so in your constructor, you need to make a new array of type E. Right? So you go ahead and write new, and then E, and then your square brackets. And then when you're looking at Eclipse, Eclipse complains, right? Or your compiler complains. Right? Your compiler will tell you this is an error. You're not allowed to make an array of generic type. Right? And so you say, well, that's awkward. Right? Okay, so in Java, you're not allowed to make an array of generic type. So I can't write new E here. Right? The solution is to make an array of object instead. Right? Because remember again, object is the parent class or the base class for all object types in Java. Right? So go ahead and change that to big O object. Right? So instead of big E, it's big O object now. Right? And now when you write new object, well, the compiler is perfectly happy with that. Right. Okay, so why doesn't this work? So the reason this doesn't work is because if the language allows arrays of generic type, then it's very easy to break code that uses those arrays. So arrays in Java are said to be, there's this term covariant. Don't memorize this term, right? I'm just telling you what this term is. I'm just using this to be complete, right? So Java arrays are said to be covariant. So if you have if sub is a subtype of super, right? So superclass, subclass, then with arrays, an array of sub is also a subtype of array of super, right? So in other words, if I have an array of object, right, then an array of string is considered to be a subclass of an array of object, right? In other words, an array of string is substitutable for an array of object. Right? And so if this was just object in string, I think most of you would be perfectly happy with that. Right now I'm telling you if it's an array of object and an array of string, this is also an inheritance relationship. Okay, so if you allow this to happen, so because of this fact, weird things happen. Right? So does this compile? Right? Now remember how this works in Java, right? So left-hand side, declared type. Right? Right-hand side, actual type. Right? The actual type has to be substitutable for the declared type. Right? So is an array of integer an array of object? Well, according to this picture, the answer is yes. So this compiles. Right? That lets you store an array of one integer in OBJS. So the answer is yes. Does that work? Right? So what is the type on the left-hand side? Well, it's an array of object. Right? OBJS is an array of object. So OBJS0 is an object reference. Right? Can I store a string in an object reference? The answer is yes. You can store a string in an object reference. Right? Strings are substitutable for objects. Right? So that also compiles, but notice the problem here. It's actually an array of integer. Right? So this compiles. Does it run? The answer is no, it doesn't run, right? So this compiles, your program builds no problem. When you go to run your program and you hit this line of code, suddenly you get an exception, right? Now the Java virtual machine realizes, hey, you're trying to store a string in an integer, and that doesn't work, right? And so this blows up on you right away. Right? So generics in Java are not covariant, right? So they are invariant. So for any two distinct types, T1 and T2, right, a list of elements of type T1 is not related at all to a list of element types of T2. Right? So here, if I have a list of object and a list of string, this relationship no longer holds. Right? I cannot store a reference to a list of string in a variable that is a list of object. Right? That does not compile. Right? And the fact that this doesn't compile stops stuff like this from happening, right? So that doesn't compile. So the reason it doesn't compile, again, is all because of this type safety, right? The language designers wanted to make sure that stuff like this couldn't happen to you when you're using the generic types. Right? Okay, so that's the explanation to why arrays behave the way they do in Java. Right? So when you're implementing a generic type with an array, you can't use the generic type, the generic element type for the type of the array, right? It's always an array of big O object. Okay, so push and pop for the stack, very small changes now, right? So push now takes in an element type of type E, right? Our generic type. This used to be int, right? It used to be an array of int. So now when I have to resize the array, I make a new array of object. Right? That's the only change on this slide compared to the int stack implementation. Right? What about pop? So pop, the only change is that when you go and get the element to return back to the caller, right, you have to remember that the element type is actually a big O object, right? Because that's what our array is. Right? I know, however, though, back in push, right, push always takes in an element of type E. Right? So I know for a fact that our stack, that our array is always holding elements of type E. Right? So when I go and get an element out of the stack, right, I know for sure I can safely cast it to type E. right? So again, remember this is a stack of object, this is an array of object, right? The caller wants back an element of type E, so I have to take the element and cast it to type E here, right? This cast is always safe because the only way you can add something to the array is by adding an element of type E to the array. Right? But that's the only change, right? I need this cast here, and the element type is now E instead of int. Right? And that's it. So there's your stack there's your generic stack now. Right? Almost no changes. Right? The only change you need to make are your stack is now a stack of object rather than a stack of int. Right? Everywhere you used to say int element, it's now E element. Right? When you're getting something out of the array, you have to cast the element type to E, right? And otherwise, there's no changes. So converting an existing class to a generic class is typically very simple. Similarly, converting an interface to a generic interface is also very simple, right? There's the original stack interface that dealt with stacks of strings, right? If I want to make this a generic interface, well, that's it, right? Insert your element type, your generic element parameter here, right? Change string to E here, and change string to E there, right? And now you've got a generic interface, right? And so converting an existing class to a generic class or interface to a generic class or interface, typically all you have to do is change some type names, right? And here I've changed string I've changed string to E, right? And added the generic type variable there. Okay, to complete the implementation of the array stack class, right, so that it's completely generic, right, all you do now is say that it implements the generic interface. Right. Wrong way, here we go. So array stack E now implements stack E, right, and that's it. And so there's the conversion of what used to be only a stack of int to a class that can now be a stack of anything, right, where the anything is a type that's specified by the user. Okay, any questions about creating a generic type? All right. So that was 27. So if you go on to OnQ, I made some changes on OnQ last night. So that was 27. Okay, so the existing slides 28 through 34, we're not going to cover this term. There's not enough time to cover them. And so I did add this new lecture set here, but it's really just cobbled together from some of these other lecture slides. So I now want to talk about how do you implement a list in Java. Right? And we've learned about generics, so we might as well start by implementing a generic list. Right? And in doing this, basically we're going to review how do you use an array to represent a resizable container. Right? And if we get to it, we'll also see, we'll probably see the beginnings of how to implement a list using a linked sequence of nodes to create what's called a linked list. All right, so remember what a list is. So a list represents a finite collection of elements held in a linear sequence. Every element has an index, right? So you can access the element via its position. And we used ArrayList quite a bit in this course. Right? It's useful to study how these lists can be implemented. It tells you something about the computational complexity of the list operations, right? And why they have the complexity that they do. So the list interface in Java is pretty big, so I don't want to implement the whole interface. So I'm going to implement a reduced interface for our lists. Right, and so we're going to have the 7 or 8 methods here. We'll include iterator. Right? All right, so size and is empty, right? How many elements are in the list, right? Is the list empty? So does it have does it have at least one element? Right? Getting and setting an element by its index. Right? Adding to the end of the list, adding to the middle, and removing from perhaps the middle of the list. Right? Now, the first 5 methods size is empty and add are the same as size is empty and push for a stack, right? They're exactly the same, right? So this corresponds to push in stack, right? Size in is empty, how many elements, right? And is the list empty or not, right? Get and set are very easy to implement. So the first 5 methods should not be new to any of you, right? Adding to the middle or removing from the list, these are new, right? Also, implementing an iterator over a list will also be something new. Okay, so there's our interface, right? So I've got this interface called sList for simple list, right? It's generic, so it's a list of one element type E, right? We're going to let our list implement the iterable interface, so that lets people write a for each loop over our list, right? And remember, by implementing that interface, that means we must have this iterator method in our class, right? So we're probably also going to implement an iterator as well. All right, so an array-based generic list is almost identical to an array-based generic stack, right? The only thing that's different is inserting into the middle and removing from the middle of the list, right? Okay, so if you want to insert into the middle of a list, right? When you insert into the list, that doesn't overwrite the element that you're inserting at, right? So I want to insert an element at index 4 in the list, right? So I'm not replacing the element at index 4, right? I want to insert at this index. So to insert at this index, I need to move the elements at indexes 4 through 8 somewhere in the list so that I can squeeze in a new element here, right? So I need to move those elements in red one position to the right, right? By moving them one position to the right, that frees up the element at index 4. So now I can add my new element at that index. When you're using this version of add, so the insert version of add, right? Typically, the Java's version of a list lets you add at the element one past the end of the list. So in other words, Java's add method will let you add at index 10, right? Even though there is no element at index 10, right? So that index 10 is not valid for the list containing those elements, right? But Java's add method allows this to happen, right? And it simply interprets that as adding to the end of the list, right? To add at the end of the list, that's easy. We're just going to call the other version of add, right? So the version of add where you only specify an element always adds at the end of the list. Right. So what if you want to remove an element from the end of the list? From the middle of the list, right? Or anywhere for that matter, right? So if I want to remove the element at index 4, right? I don't want to leave a hole in the list, in the array, right? And so in other words, I don't want to leave a blank spot in the array, right? I want to fill that up, and the way I'm going to fill it up is I'm going to move all the elements to the right, the ones shown in red. I'm going to move them one position to the left, right? So that overwrites the removed element, right? Shuffling all the other elements one position to the left, right? The element that used to be at index 10 is now at index 9. Right? Okay, so those two pictures, right? We're adding into the middle and removing from the middle. Hopefully it makes it clear that inserting or removing an element from the middle of a list has worst case complexity of big O(n). Right? Why? Because you have to move up to n minus 1 elements every time you do this operation. Right? So for example, if you want to remove the first element of the list, right, you're moving the n minus 1 elements to the right, one position to the left. Right? And so the worst case complexity is going to be O(n). So if you are solving a problem using an array-based list, if you're solving a problem that involves a list and you need to remove from the middle of the list or insert repeatedly in the middle of the list, you probably don't want to use an array-based list. Right? Every time you try to insert or remove from somewhere in the middle, right, the complexity becomes big O of n. All right, so how do you implement this thing? So basically, you just take your stack implementation and copy it, right? So our simple array-based list, right, is going to implement our simple list interface. Right? Just like a stack, it's going to have an array of objects to hold the elements. Right? So my array here is just called ARR. Right? Just like a stack, we're going to record how many elements are in the list. Right? So that's going to be stored in size. Right? The constructor, exactly the same as the stack constructor. Right? We make an array of some default size, so in this case 16, right? And then we set the size to 0. Right? So the list created with the no argument constructor can hold up to 16 values before we have to resize the list. Right? Or resize the array, sorry. Size is easy. We have a field that represents the size, so I can just return the size. Right? So what about add? Add is exactly the same as push. Right? It's the exact same method. So in push, right? Remember what we tested for in push? We tested, is the array currently full? Right? So in other words, is the size of the array is the size of the list equal to the length of the array? Right? If it is, I have to resize the array. Right? And we resize the array using copy of. Right? So copy this array, returning a new copy of the array that is twice as long. Right? And I'm just going to store that back in this array. Right? So that resizes the array, and now I want to add the element to the end of the array. So the end of the list. Right? The end of the list is at elements, one past the end of the list is at index this.size. Right? So you just set the array element at this.size to the newly added element. Right? And don't forget, increase the size of the list by 1. Right? And that's the add method. Right? It's identical to push. All right, so the other methods that we want to implement, they're all index-based. Right? And so we want to make sure that the user is always using a valid index. And there's several methods that are index-based. So I don't want to repeat the validation code in each method. I'm going to create a separate method that does the validation for us. Right? So checkIndex checks if that index is valid for this list. Right? If it's not, it throws an exception. Right? So what are valid indexes for a list? So in Java, they have to be 0 or up between 0 and the size of the list minus 1. Right? So if the index is negative, we throw an index out of bounds exception, indicating that you used a negative index. Right? The index has to be less than the size of the list. So if the index is equal to or greater than the size of the list, right, we throw an index out of bounds exception, indicating that the index is too high. Right? So every time I need to check an index now, I can just call checkIndex. All right, so what does get do? So get returns the element at that index. Right? How do you get an element out of an array at that index? Well, I just write this array index. Right? Before you do that, though, make sure you check the index in case the user has used an incorrect index. Right? Don't forget, our array is an array of big O object. Right? The user is expecting back an element of type E, so you need the cast here to convert the reference to an object to a reference of type E. Right? Set sets the element at that index to elem. Right? So again, check to make sure. Set also returns the previous value stored in the list at that index. Right? So to get the previous value stored in the list, I'm just going to call get. Right? Calling get has a nice side effect for us. Get also checks the index for us, so I don't have to check the index here in set. Right? Calling get will do that for us. Right? Now I need to replace the element at this index. So to replace the element at that index, you just go into the array at that index and set it to elem. Right? And then return the previous value as old. Okay, so there's 5 of the 7 methods that we need to implement, or 8 that we need to implement, right? We did that in like 5 minutes, so that's pretty easy. Adding to the end of the list, adding somewhere in the middle of the list is slightly trickier. It's not that much trickier, right? You just have to remember you need to shuffle some elements over to the right. So add at an index This is basically insert, right? So insert into the list. Right? Now remember I said that you can add at the end of the list, right? So if the index is equal to the size of the list, right? Technically that's not a valid index, it's one past the end of the list, right? Java allows that, so we're just going to add to the end of the list. I can add to the end of the list by calling add. Right? Okay, so if we're not adding at the end of the list, right, I now need to check the index to make sure it's valid. Right? So call check index, right, to test if the index is valid. If it's not, we'll throw an exception here. Okay, if it is valid, so now we want to insert into the middle of the list. So I need to shuffle elements to the right. Right? The only slightly tricky thing here is that you have to write the loop in a certain way. Right? So if you want to move elements to the right in an array, you can't start at index 0 and go up. Right? If you start at index, you can't start at the smaller index and go up. Right? If you start at the smaller index and go up, so I'm going to start at index I, right? I'm going to move that element one position to the right, right? So that's going to overwrite the element at index I plus 1, right? And now I've lost an element from my list, right? You have to start at the end of the list and move the elements over from the end of the list, right? So starting at the end of the list, which is at index size minus 1, right? Going down to the insertion index, right? So greater than or equal to, right? I want to count down each time, right? So starting at the rightmost value, right? That's the rightmost value, right? Store it in the position 1 to the right, right? Going all the way down to the insertion index, right? So whenever you're playing around with indexes, right? So whenever you're using I here to index into an array, right? You always want to ask the question, are the indexes valid, right? So is I valid, and on the left-hand side, is I plus 1 valid? Right? So what's the largest value for I? It's this size minus 1. So I know for sure that's valid. Right? I plus 1, the largest value is going to be this size minus 1 plus 1. So that's this dot size. Right? So is that a valid index? Right? And the answer is maybe not. Right? This may not be a valid index, right? Missing from this, right? Notice here, there's actually 2 errors in this slide, right? So notice the problem here is that if you're inserting into the list, right, there may not be enough space in the array to hold the new element, right? So after you check the index, you also have to check whether or not you need to resize the array, right? So right there. Right? Before you start to move elements around, check if you have to resize the array. If you do, resize the array. Right? Then proceed with the rest of the code. Right? I guess you have to check the smallest value for the index too. Right? So the smallest value for the index is going to be index. And we've already validated the index back here. Right? So we know for sure that the smallest value of I is going to be valid. Right? I plus 1 is 1 bigger than that, so that's also valid. Once I've moved all the elements to the right, go ahead and update the element at that index. Right? Don't forget, you just added something to the list, so increase the size by 1. Right? So error number 1, right? Make sure there's capacity in the array, resize the array if you have to. There's a second error. So does anybody see the second error? If you're looking at the version of the slides that are posted, that version has the second error corrected. Right? So the second error is, right, if we're adding at the end of the list, right, we call add to add the element to the end of the list, right? And then we do all of this, right? So check index now succeeds because we just added a new element to the list, right? So now the index that was at the end of the, one past the end of the old list is now the element at the end of the list, right? So that now passes, and then we go ahead and insert the element a second time, right? So the other error on this slide is that if you're going to add the element using add to return after you do that, right? So there's mistake number 2. That's corrected on the versions that are posted online. So that's inserting into a list. Removing from a list, all you have to do is move the elements one position to the left to overwrite the element that you're removing. So when you're moving to the left, you can start at the lower index, right, and count up. Right. Remove also returns the element that was removed. Right. So it's useful to call get here. Right. Get validates the index for us, and then it also lets us remember what is the element that we're about to remove. Right. Now shuffle the elements one position to the left, right, starting at index I plus 1. So I is going to be the element that I am moving one position to the left. Right. So I want to start at the element to the right of the position that I'm inserting at. Right. So that's at element index I plus 1. Right. I want to move all the elements to the right of that one position to the left. Right. So I want I to be less than the size of the list. Right. And now move the element at index I one position to the left. So go down to I minus 1. Right. Again, you're indexing into an array. Right. So make sure, ask yourself the question, are these indexes always valid? Right. So what is the smallest value of I? Smallest value of I is index plus 1. The smallest legal index is 0. So the smallest value of I is 1. Right. So 1 is probably a valid index. Is I minus 1 a valid index? So that's 0. So the smallest index that you can use here is 0, which is a valid index for the array. Right. So that's not going to throw. If you're removing something from an array, and it's an array of reference type, which this is, right? When you remove something from the array, you should probably remove you should overwrite the element at that you're removing with the value null, right? If you, this shuffling over here doesn't actually move the elements, right? It's actually copying an element from the right to the left. So whatever was at the end of the array, right? So in other words, the element at this size minus 1, right, is still there after you've shuffled the elements one position to the left, right? So you want to remove that element. You actually really want to remove that element from the array. So you should set that to null, right? If you don't set it to null, then there's still a valid reference sitting in the array, right? And as long as there's a reference to an object, Java won't get rid of that object from memory. So in other words, if you make a list, you make a huge list and you populate it with a bunch of elements, right, and then you remove them all, Java won't get rid of all the objects that your list was referring to, right, if you don't null out the value in the array, right, because the array still holds a reference to those objects. So make sure to null it out and away you go. If you're working with an array of primitive values, you don't care, right, and you can't set a primitive value to null anyway. You've removed something from the list, so don't forget to reduce the size by 1, right? And then return the removed element, right? So implementing a list with an array is no harder than implementing a stack with an array, right? The only complications are the shuffling, right? So to remove, you need to shuffle elements to the left, right? To insert, you need to shuffle elements to the right, right? Otherwise, there's nothing significantly different compared to a stack. So that's a good place to stop because the next topic is how do you make an iterator for this thing, right? And that's going to take a little bit of time to explain. So we'll stop there for today and pick this up again on Thursday.